Ever wondered how a quantum computer is so powerful? It all starts with the qubit. And like a normal computer bit, which is just a simple on or off switch, a 0 or a 1, a qubit is something much stranger. Think of a spinning coin. Before it lands, it has not just heads or tails, it has in a state of both at the same time. That's a qubit. It can be 0, 1, or a combination of both, all at once. This is called superposition, and it's the secret to their power. This means a single qubit can explore multiple possibilities simultaneously. And when you link them together through a process called entanglement, their power grows exponentially. 2 qubits can test for states at once. And just 50 qubits can represent more states than the world's biggest supercomputer. Qubits are the building blocks for a new era of computing, promising to solve problems we can only dream of today. Follow to learn more. Hello everyone and welcome back to our quantum journey. Today, we're diving into one of the most important ideas in quantum computing, the qubit. If you've ever wondered how quantum computers process information differently from ordinary computers, it all begins with this tiny but incredibly powerful building block. A qubit is not just a quantum version of a classical bit. It is something entirely new, something that behaves in ways our everyday world never shows us. And by the end of this video, you will understand exactly what a qubit is, how it works, and why it's the key to the future of computing. Let's start with what we already know. In a classical computer, the laptop or phone you use every day, everything is built from bits. A bit is like a simple switch that can be either off or on, 0 or 1. That's it. Every message, every video, every game, every document is built from billions of bits switching between these two states. A qubit, however, is a quantum bit. It is like a switch that can be off, on, or something far more strange, both off and on at the same time. This is possible because qubits obey the laws of quantum physics, not classical physics. In the quantum world, things don't behave like everyday switches. They behave more like waves, probabilities, and strange combinations of states. Imagine holding a coin. When it's lying on the table, it's either heads or tails, just like a classical bit. But when you spin the coin in the air, before it lands, it isn't strictly heads or tails. It's in a sort of in-between state. That spinning state analogy gives us a simple picture of a qubit. While a classical bit must be either 0 or 1, a qubit can be in 0, 1, or a superposition of both 0 and 1. This ability to exist in multiple states at once is what gives qubits their extraordinary power. Another easy way to picture a qubit is to think about a light dimmer switch instead of a simple on-off switch. A classical bit is only full off or full on. A qubit is more like a dimmer that can take any setting between off and on. But here's the catch: a qubit isn't just somewhere between 0 and 1. It is a combination of 0 and 1 at the same time. It's not a halfway state, it's a multi-state probability wave. This means when we measure a qubit, it collapses and becomes either 0 or 1, but before measurement, it holds information in a much richer form. To make this even simpler, imagine you're trying to guess what's inside a closed box. A classical bit can store only one answer, yes or no. A qubit stores yes and no together. So when a quantum computer works on a problem, it doesn't test one solution at a time. A single qubit explores multiple possibilities at once. Multiply this by many qubits, and you see why quantum computers can become exponentially more powerful than classical ones. Now let's talk about the physical side of qubits. Qubits are not imaginary software objects. They are real physical systems. Scientists use many different technologies to build qubits, such as photons of light, trapped ions, superconducting circuits, quantum dots, or even defects inside diamonds. Each of these systems behaves according to the rules of quantum mechanics and can store quantum information. For example, in superconducting qubits, the type used by Google and IBM, tiny electrical loops cooled close to absolute zero create electrons that behave as a single quantum system. Their energy levels represent the 0 and 1 states of a qubit. Another example is ion-trapped qubits, where individual atoms are held in place by electromagnetic fields. The internal energy states of the atom act as the qubit. Imagine holding a single atom, controlling it with lasers, and making it behave as the building block of a future supercomputer. That is the reality of quantum computing technology today. Here is where qubits become even more powerful. They can interact with each other through a quantum phenomenon called entanglement. When qubits become entangled, the state of one qubit instantly affects the state of another, no matter how far apart they are. This means qubits do not just store data individually. They form networks of interconnected information. A system of entangled qubits can represent far more information than the same number of classical bits. 2 qubits can represent 4 states at once. 3 qubits can represent 8 states. 10 qubits can represent over 1,000 states. And 50 qubits can represent more states than the largest supercomputer can handle. Let's bring this to a simple example. If you flip a classical coin, you get one outcome. If you flip 2 classical coins, you get 2 outcomes. But if you use quantum coins, qubits in superposition and entanglement, you don't get a few outcomes. You get a whole cloud of possibilities all being evaluated together. This is why quantum computers can solve certain problems, like chemistry simulations, optimization, cryptography, and machine learning tasks, incredibly faster than classical computers. But qubits are not easy to control. They are extremely sensitive. Any noise like heat, vibration, or electromagnetic waves can destroy their quantum state. This is called decoherence, and it's one of the biggest challenges in quantum computing. That's why quantum computers sit inside huge refrigerators, shielded from everything, operating at temperatures colder than outer space. Scientists are working on error correction techniques to keep qubits stable long enough to perform useful calculations. Even with these challenges, the progress is amazing. We're at the beginning of a new technological revolution. Qubits are to quantum computers what bits were to the first classical computers decades ago. They represent the next evolution of information itself. And the more qubits we build and the better we make them, the closer we get to unlocking computational power that will change science, medicine, cybersecurity, engineering, and artificial intelligence. So now you understand what a qubit truly is, not just a yes or no switch, but a quantum system that can exist in many states at once, interact with other qubits, and create computational possibilities far beyond the limits of classical machines. We are entering a world where computers no longer think in zeros and ones alone, but in an entire universe of probabilities. If you're enjoying this quantum series and want more simple, powerful explanations, make sure to hit that subscribe button. Stay tuned because the next videos will take you even deeper into how quantum computing actually works, step by step. Thanks for watching, and I'll see you in the next one.